The cosmos is often viewed as an endless web of dynamic activity, where countless mini-cosmic eruptions, sometimes dubbed Little Big Bangs, play a role in shaping the ever-expanding universe. Among the mysteries floating in this immense expanse is Pluto, once hailed as the ninth planet of our solar system. Those who studied astronomy before 2006 would recall Pluto being listed without dispute among the traditional planets. But that changed dramatically almost 2 decades ago when the International Astronomical Union, IU, altered Pluto's status, reclassifying it as a dwarf planet. That controversial decision, made in 2006, did not end the debate. Recent discussions have reignited within the IU, largely driven by powerful new visuals and scientific findings from NASA. These revelations come courtesy of groundbreaking tools like the James Webb Space Telescope, JWST, and they bring fresh perspectives on Pluto's behavior and characteristics, prompting many to question whether its demotion was ever justified. Our quest to understand Pluto is part of a larger journey through the mysteries of the cosmos. Since the historic Apollo 11 landing, human interest in exploring the universe has only grown stronger. From pondering the birth of the universe in the Big Bang to understanding how one planet among many developed life, our curiosity has been insatiable. That same curiosity now turns toward the icy frontier of our solar system, where Pluto sits as a symbol of how much we still have to learn. The JWST plays a central role in this pursuit. It stands as one of NASA's most sophisticated instruments yet, capable of capturing highly detailed images and peering through cosmic dust to study ancient galaxies, black holes, and distant planetary bodies. Though designed primarily to look into the past, the telescope is also dramatically improving our comprehension of present-day solar system members like Pluto. Pluto's reclassification sparked 2 opposing viewpoints within the scientific community. Some researchers felt the IAU acted too quickly, especially given the lack of detailed data at the time. Others accepted the new designation, arguing that it was based on then current planetary criteria. Most, however, remained cautious, waiting for more information before drawing firm conclusions. That information began arriving in earnest with NASA's New Horizons mission. Launched in 2006, the same year Pluto lost its planet title, New Horizons reached its target in July 2015 after an extraordinary 3 billion-mile journey. It became the first spacecraft to closely study Pluto and its moons, returning a wealth of data that changed everything scientists thought they knew about this distant world. The mission produced roughly 6.25 gigabytes of data over 15 months, including detailed images and surface readings of Pluto and its 5 known moons, Charon, Nix, Hydra, Kerberos, and Styx. What it revealed was astonishing. Pluto was not the frozen, inactive rock many had believed it to be. Instead, the surface showed signs of dynamic processes, from flowing glaciers to shifting atmospheric conditions. This came as a shock to many in the astronomical community. Pluto, rather than being a static remnant of early solar system history, was alive with activity. Enormous nitrogen ice fields, mountainous terrain made of solid water ice, and an evolving, albeit thin, atmosphere demonstrated that Pluto was undergoing changes on a planetary scale. These findings contradicted previous assumptions that small celestial bodies in the outer solar system would be geologically dead due to their limited internal heat and distance from the Sun. Pluto's activity indicated otherwise. It had heat sources, complex surface changes, and potentially even a subsurface ocean. The definition of what constitutes a planet began to feel increasingly inadequate. The New Horizons mission wasn't just a milestone in technical achievement. It was a philosophical shift in how scientists view icy bodies beyond Neptune. Its success gave NASA a compelling reason to push further into the Kuiper Belt, a region teeming with ancient remnants from the solar system's formation. The James Webb Space Telescope has since taken Pluto exploration to the next level. Its advanced instruments provide researchers with enhanced imaging and spectral analysis capabilities, allowing for even deeper study of Pluto's atmospheric interactions, geology, and potential for subsurface activity. One particularly intriguing discovery centers on Sputnik Planitia, the left side of Pluto's iconic heart-shaped feature. This vast nitrogen glacier, stretching for millions of square kilometers, isn't just a pretty landmark. It's key to Pluto's shifting spin. Its mass is believed to have tilted the planet's crust over time, a phenomenon known as true polar wander. Sputnik Planitia wasn't located where scientists initially expected. Its placement indicated a massive imbalance in Pluto's internal structure, forcing a change in its rotational orientation. The gravitational relationship between Pluto and its largest moon, Charon, intensified this shift. These two bodies are locked in a synchronous orbit, meaning they always face each other. Yet the glacier's enormous mass appears to have pulled the axis off kilter, reshaping how Pluto rotates in space. This revelation has major implications for our understanding of planetary dynamics. It suggests that Pluto, though small and distant, is internally active and capable of major geological transformations. The discovery also implies that other dwarf planets or Kuiper Belt objects could be similarly complex, opening up new possibilities for exploration. The more scientists observe Pluto, the more they find it challenges outdated assumptions. Educational materials are already being revised to reflect these discoveries. Textbooks that once described Pluto as a cold, lifeless rock are now including data on its atmospheric changes, surface shifts, and internal heat. These revisions are more than cosmetic. They're part of a fundamental shift in how we define and categorize celestial bodies. New Horizons also illuminated another unexpected aspect. Pluto's heart is not just metaphorical. Its internal heat and the movements of Sputnik Planitia are actually driving many of the geological processes on the planet. The glacier is believed to be up to 4 kilometers thick, exerting enough pressure to shift the entire crust over time. This gravitational force affects more than just Pluto's rotation. The tidal pull between Pluto and Charon appears to be influenced by the glacier's position, further complicating the planetary dynamics of this dwarf planet. Essentially, Pluto is being reshaped by the weight of its own icy heart, a revelation that underscores the planet's geophysical complexity. Additionally, scientists discovered that Pluto's axis tilt may also be influenced by its mass imbalance. The core of Sputnik Planitia may play a significant role in how the planet spins, proving that even minor celestial objects are susceptible to powerful geological processes. This supports the idea that Pluto's planetary status deserves reconsideration. Although Pluto is inhospitable and incapable of supporting life as we know it, its role in the grand cosmic picture is far from insignificant. In fact, Pluto is proving to be one of the most scientifically valuable objects in the outer solar system. Despite its small size and distant location, Pluto is helping astronomers develop a deeper and more nuanced understanding of icy celestial bodies, planetary evolution, and the broader mechanics of our solar system. Every bit of data collected from missions like NASA's New Horizons and observations made through the James Webb Space Telescope, JWST, is contributing vital insights that challenge old assumptions and push the boundaries of what we know about planetary science. When New Horizons completed its flyby of Pluto in July 2015, it sent back stunning images and a treasure trove of data that completely transformed our perception of this distant dwarf planet. We had long assumed that Pluto was a frozen, inactive world, little more than a remnant of the solar system's formation. But those assumptions were swiftly overturned. Instead of a lifeless rock, scientists discovered a complex and dynamic world, complete with flowing nitrogen glaciers, towering water ice mountains, mysterious atmospheric haze, and even suggestions of subsurface oceans. These unexpected features made one thing clear. Pluto is geologically active, and this activity is not only fascinating but also important for comparative planetology. Now, with the James Webb Space Telescope offering even sharper, more detailed observations, Pluto is once again under the scientific spotlight. The JWST's unparalleled sensitivity in the infrared spectrum allows researchers to peer through cosmic dust and analyze Pluto's surface composition, thermal emissions, and atmospheric changes in ways that were previously impossible. These combined efforts are helping scientists refine their models of how distant, icy bodies form and evolve, models that could also apply to other objects in the Kuiper Belt and beyond. Pluto serves as a window into the early solar system, preserving clues that have been lost on larger, more geologically evolved planets. Understanding its composition and behavior sheds light not only on Pluto itself, but also on the wider category of dwarf planets and icy moons that populate the outer solar system. These findings are helping to rewrite the narrative of what planetary bodies can be, showing that complexity and geological richness are not exclusive to large or Earth-like worlds. This growing body of evidence serves as a compelling reminder that the universe is anything but static. It is in a constant state of motion and transformation. The further we reach with our technology and curiosity, the more we uncover about the surprising vitality of even the most remote corners of our cosmic neighborhood. Pluto may not support life, but it does support discovery, and in that sense, it remains one of the most compelling bodies we've yet explored. Its story is still unfolding, urging us to keep looking, questioning, and expanding the frontiers of human knowledge. Moreover, our exploration tools are advancing at lightning speed. Private companies like SpaceX and Blue Origin, along with public agencies like NASA, are driving a new era of space discovery. Instruments like JWST have unparalleled sensitivity and precision, allowing us to interpret massive data sets with unprecedented efficiency. The technological leaps we've made in just the past 2 decades are enabling us to peer further and more clearly than ever before. Our growing understanding of planetary geology and formation has been revolutionized. Where once we believed only large planets could support complex geology, we now know that even distant, icy worlds like Pluto can be vibrant, evolving entities. These revelations are changing how we approach the classification of celestial bodies, urging a more fluid and evidence-based approach rather than rigid definitions. Ultimately, Pluto's narrative has evolved from that of a forgotten outcast to a symbol of possibility. It defies expectations and dares us to broaden our scientific frameworks. Thanks to New Horizons and JWST, we are now piecing together a more accurate and dynamic view of the outer solar system. The line between dwarf planet and full planet is beginning to blur. Pluto demonstrates that size alone doesn't determine significance. Its complexity, activity, and influence all suggest that it is far more than a minor object drifting at the edge of our solar system. In conclusion, the mystery of Pluto serves as a lens through which we understand broader cosmic principles. It reflects how scientific thought evolves with evidence and reminds us that the universe often resists simple explanations. As space technology continues to advance, and as new missions reach even farther into the unknown, Pluto stands as a shining example of why exploration matters. It's not just about labeling planets. It's about embracing discovery in all its unpredictable, fascinating glory. And that, perhaps, is the most planetary quality of all.